I am working on the chat integration. So I need um, Aviate prerequisites. This is my sandbox. Connect or create. That's real quick. Quick start. Hmm. Right. Okay, now I've been approved, so create a Weavit cluster. When you log into the Weavit WCS web console, the dashboard tab lists your clusters. There are no clusters when you log into a new account. WCS has short-term sandbox clusters and permanent managed clusters. Create cluster. Uh, how do I get back to that window? Oh, I gotta share this tab. Sorry. Yeah, create a cluster. Free sandbox or managed cluster. $25 a month, so allow us to do it free. 14 days lifetime, public stack, public Slack rather, single availability zone monitoring, free support. What do we call this? Enable authentication. Or ODIC issuer. Static API key you can use to use authenticate. Alright, I'm done already. Alright, we're gonna connect. Um, G2. GraphQL interface. Mm. Sorry, I'm tired, and I keep making a mistake and just kind of tuning out because I'm tired. I didn't get enough coffee before I started. What? What errors? What's the problem here?
Well, that's just great. Distracted. Just setting up payment information. That's good so far. Okay, that just renders the page. I mean, at least that's running. But it should be like. Hmm. All right, come on, figure this out. Can't get rid of them. Oh, come on. Fuck. last Weaviate. Just getting some soda stream. All right, now what? First, start by duplicating the studio template by clicking on Open Template. The studio would launch a new tab. It's Open Studio, actually. This studio contains 3 different ways to run the chat with your code rag application: simple Python scripting, Jupyter Notebook, or the code to run a Streamlit app. Yeah. So this is the Streamlit app. Note that the model will be loaded into memory after running one of the 3 loadable files. This might result in an memory issue if you run another file. Okay, set up LLM and embedded model. Mistral. That's easy enough. Couple Python commands. Where do we put it? I don't know where it's supposed to be. Okay, here it is. Yeah, it's already done. Unless I'm going somewhere else. No files from GitHub. Sample directory reader. Come on. All right, I need to come back to this in a few minutes. Just need to take a break. But I'll be back to use the washroom, and grab a little bite to eat. But we're getting there, okay? So I have the database server thing. I have to set some API keys, and I have to invalidate my Lumen credit card again because I exposed it via the live stream. And I have to generate the API keys again because they're supposed to be secret. So those will be able to be changed right away. So that's what I'm doing right now. Gotta cancel my Lumen card because it got exposed. That's the dangers of doing live streams with real data. Not like I have anything you can steal right now in the bank. I can't believe I have to cancel this thing again. Maybe I'll just leave it. I mean, nobody saw the three-digit pin, right? So, like, who cares then? Oh, they'll just brute force the Lumen pin, the 3 digits code. Shit. Fine, fuck off. I'm changing it. All right, my card's locked, so nobody can steal anything there. But anyway, okay, that part's done. I'm gonna change the API keys and come back with the rest of the chat app. And I'm sorry for being so tired, but it's early morning and I was up very early trying to just get through some of the documentation I have to do for my business and some other tutorials. But I will get back to this shortly. So we'll say in about half an hour, about 7:30, 7:35. I'll be back. I'm just gonna I'm gonna play a video for the stream for the Weaviate so that people can learn a little bit about vector storage database from Weaviate. This is a vector database in Go. I didn't know it was in Go.
The database at all. It may be even worse or even matter to build a database in Go when most are built in. Okay, closer. Okay. Okay, cool. Let me start over in case you didn't hear it. So, hi, my name is Etienne. Welcome to our mad journey of building a vector database in Go. So building a database at all could already be pretty mad. Doing it in Go when most are built in C or C++ could be even madder or even more exciting. And we definitely encountered a couple of unique problems that led us to create creative solutions. And there's lots of shouts out in there and also a couple of wish lists. So we just released Go 1.20. And of course, the occasional madness. So let's get one question out of the way right away. Why does the world even need yet another database? There's so many out there already, but probably you've seen this thing called ChatGPT, because that was pretty much everywhere, and it's kind of hard to hide from it. And ChatGPT is a large language model, and it's really good at putting text together that sounds really sophisticated and sounds nice, and sometimes is completely wrong. And so in this case, we're asking it, is it mad to write a database? And go, I might disagree with that. But either way, basically, we're now in a situation where on the one hand, we have these machine learning models that can do all the cool stuff and do this sort of interactively and on the fly. And on the other side, we have traditional databases. And those traditional databases, they have the facts, because that's kind of what databases are for, right? So wouldn't it be cool if we could somehow combine those two? So for example, on the query side, if I ask Wikipedia, why can airplanes fly? Then the kind of passage that I want that has the answer in it is titled The Physics of Flight. But that is difficult for a traditional search engine, because if you look at keyword overlap, there's almost none in there. But a vector search engine can use machine learning models, basically, that can tell you these two things are the same. And searching through that at scale is a big problem. Then there's that sort of ChatGPT side, where you don't just want to search through it, but maybe you also want to say, like, take those results, summarize them, and also translate them to German. So basically not just return exactly what's in the database, but do something with it and basically generate more data from it. And that is exactly where VV8 comes in. So VV8 is a vector search engine, which basically helps us solve this kind of searching by meaning instead of keywords without sort of losing what we've done in 20 plus years of search engine research. And now, most recently, you can also interact with these models such as ChatGPT, GPT-3, and of course also the open source versions of it. So VV8 is written in Go. Is that a good idea? Is that a bad idea? Or have we just gone plain mad? So we're not alone. That's good. So you probably recognize these things. They're all bigger brands at the moment than VV8, but VV8 is growing fast. Some of those vendors have really great blog posts where you see some of the optimization topics and some of the crazy stuff that they had to do. So if you've contributed to one of those, some of the things I'm going to say might sound familiar. If not, then buckle up. It's going to get mad. So first stop on our mad journey, memory allocations, and that also brings us to our friend, the garbage collector. So for any high-performance Go application, sooner or later, you're going to talk about memory allocations. And I definitely consider a database a high-performance application, or at least I consider VV8 a high-performance application. And if you think of what databases do, in essence, basically, you have something on disk and you want to serve it to the user. That's one of the most important user journeys in a database. And here, this is represented by just a number. So I went for uint32. So that's just 4 bytes on disk. And basically, you can see sort of these 4 bytes. If you parse them into Go, they would have the value of 16 in that uint32. And this is essentially something, very much simplified, that a database needs to do, and it needs to do it over and over again. So the standard library gives us the encoding/binary package, and there we have this binary.read method, which I think looks really cool. To me, it looks like idiomatic Go because it has the io.reader interface, like everyone's favorite interface, and you can put all of that stuff in there. And if you run this code and there's no error, then basically you get exactly what you want. You could turn those sort of 4 bytes that were somewhere on disk, turn them into our in-memory representation of that uint32. So is this a good idea to do that exactly like that? Well, if you do it once or maybe twice, could be a good idea. If you do it a billion times, this is what happens. So for those of you who are new to CPU profiles in Go, this is madness. This is pretty bad. So first of all, you see it in the center. Parsing those 1 billion numbers took 26 seconds. And 26 seconds is not the kind of time that we ever have in a database. But worse than that, if you look at that profile, we have stuff like runtime malloc gc, runtime memmove, runtime madvice. So all these things, they're related to memory allocations or to garbage collection. What they're not related to is parsing data, which is what we wanted to do, right? So how much time of that 20 seconds did we spend what we wanted to do? Don't know. It doesn't even show up in the profile. So, and to understand why that is the case, we need to quickly talk about the stack and the heap. So you can think of the stack as basically your function stack. So you call one function that calls another function, and then at some point, basically, you go back through the stack. And this is very short-lived, and this is cheap and fast to allocate. And why is it cheap? Because you know exactly the runtime of your variables or the life cycle of your variables. So you don't even need to involve the garbage collector. So no garbage collector, cheap and fast. Then on the other side, you have the heap. And the heap is basically this sort of long-lived kind of memory, and that's expensive and slow to allocate. And why? Because, and also to deallocate. Why? Because it involves the garbage collector. So if the stack is so much cheaper, then we can just always allocate on the stack, right? So warning, this is not real Go. Please do not do this. This is sort of a fictional example of allocating a buffer of size 8, and then we're going to say, like, yeah, please put this on the stack. And that is not how it works. And for most of you, you probably say, like, this is pretty good that it's not that it works that way, because why would you want to deal with that? But for me, just trying to build a database in Go, I said, yeah, sometimes like something like this may be good or maybe not. So how does it work? Go does something that's called escape analysis. So if you compile your code with gc flags-m, then Go annotates your code basically and tells you sort of what's happening there. So here you can see in the second line that this num variable that we used was moved to the heap, and then in the next point you see the bytes.reader, which represents our io.reader escaped to the heap. So it's 2 times we see that something happened to the, or went to the heap. We don't exactly know what happened yet, but at least sort of there's proof that we have this kind of allocation problem. So what can we do? Well, we can simplify a bit. It turns out that the binary or encoding binary package also has another method that looks like this, which is just called uint32 on the little endian package. And it kind of does the same thing. You just put in the buffer on the one side. So no reader this time. You just put in the raw buffer, basically, with the position offset. And on the other side, you get the number out. And the crazy thing is, this one line needs no memory allocations. So if we do that again, our 1 billion numbers that took 26 seconds before now take 600 milliseconds. So now we're starting to get into a range where, like, this is acceptable for databases. And more importantly, what we see on that profile, the profile is so much simpler right now. There's basically just this one function there. And that is yeah, it's what we wanted to do. So admittedly, we're not doing much other than parsing the data at the moment, but at least we got sort of rid of all the noise, and you can see the speed up. Okay, so quickly to recap. If we say a database is nothing but reading data and sort of parsing it to serve it to the user, then we do that over and over again, then we need to take care of memory allocations. And the fix in this case was super simple. We changed 2 lines of code and reduced it from 26 seconds to 600 milliseconds. But why we had to do that wasn't very intuitive. Like, that wasn't very obvious. In fact, I haven't even told you yet why this binary.littleendian.read, why that escaped to the heap. And in this case, it's because we passed in a pointer and we passed in an interface. And that's kind of a hint, basically, that something might escape to the heap. So what I would wish is, yes, this is not a topic that you need every day you write Go, but maybe if you do need this, would be cool if there was better education. Okay, so second step, delayed decoding. So this is kind of the idea that we wouldn't want to do the same work twice. And we're sticking with our example of serving data from disk, but now, well, the number example was a bit too simple, so let's make it slightly more complex. We have this nested array here, basically a sort of slice of uint64, and that's representative now for a more complex object on your database. Of course, in reality, you'd have like string props and that kind of things, but just sort of to show that there's more going on than a single number. And let's say we have 80 million of them, so 10 million of the outer slice, and then 8 elements in each inner slice, and our task is just to sum those up. So these are 80 million numbers, and we want to know what is the sum of them. So that is actually kind of a realistic database task for an OLAP kind of database. Yeah, we need to somehow represent that data on disk, and we're looking at 2 ways to do this. The first one is JSON representation, and then the second one would be some sort of binary encoding, and then there'll be more. So JSON is basically just here for completeness sake. We can basically rule it out immediately. So when you're building a database, you're probably not using JSON to store stuff on disk, unless it's sort of a JSON database. Why? Because it's space inefficient. So if you want to represent those numbers on disk, like JSON basically uses strings for it, and then you have all these control characters. You have like your curly braces and your quotes and your colons and everything. That takes up space. So in our fictional example, that would take up 1.6 gigabyte, and you'll see soon that we can do that more efficient. But also, it's slow. And part of why it's slow is, again, because we have these memory allocations, but also the whole parsing just takes time. So in our example, this took 14 seconds to sum up those 80 million numbers. And yeah, as I said before, you just don't have double-digit seconds in a database. So we can do something that's a bit smarter, which is called length encoding. So we're encoding this basically as binary, and we're spending one, in this case, 1 byte. So that's basically a uint8. And we're using that as a length indicator. So basically that tells us that when we're reading this from disk, that just tells us what's coming up. So in this case, it says we have 8 elements coming up, and then we know that our elements, in this example, is uint32. So that's 4 bytes each. So basically the next 32 bytes that we're reading are going to be our 8 inner arrays. And then we just continue. Then we basically read the next length indicator, and this way we can encode the stuff sort of in one contiguous thing. Then, of course, we have to decode it somehow. And we can do that because we've learned from our previous example, right? So we're not going to use binary.little-endian.read, but we're doing this in an allocation-free way. You can see that in the length line, basically. And yeah, our goal is to take that data and put it into our nested sort of go slice of uint64. And the code here, basically, you see we're reading the length, and then we're increasing our offset so we know where to read from. And then we're basically repeating this for the inner slice, which is just hinted at here by the decode inner function. So what happens when we do this? First of all, the good news, 660 megabytes, that's way less than our 1.6 gigabyte before. So basically just by using a more space-efficient way to represent data, we've done exactly that. We've reduced our size. Also, it's much, much faster. So we were at 14 seconds before, and now it's down to 260 milliseconds. But this is our mad journey of building a database, so we're not done here yet because there's some.
I have been watching this, by the way. I was
hidden madness
trying to get some
is
stuff.
that we actually spend 250 milliseconds
So,
decoding, while we spend 10 milliseconds
interesting, isn't it?
summing up those 80 million numbers. So again, we're kind of in that situation where we're doing something that we never really set out to do. Like we wanted to do something else, but we're spending our time on doing something that we didn't want to do. So where does that come from? And the first problem is basically that what we set out to do was flawed from the get-go. Because we said we want to decode, so we're basically thinking in the same way that we're thinking as we were with JSON. We said that we want to decode this entire thing into this Go data structure. But that means that you see we need to allocate this massive slice again. And that also means that we need to, in each inner slice, we also need to allocate again. So we're basically allocating and allocating over and over again, where our task was not to allocate. Our task was to sum up numbers. So we can actually just simplify this a bit, and we can basically just not decode it. Like while we're looping over that data anyway, instead of storing it in an array, we can just do with it what we plan to do. And in this case, this would be summing up the data. So basically, getting rid of that decoding step helps us to make this way faster. So now we're at 46 milliseconds. Of course, our footprint of the data on disk hasn't changed because it's the same data that we're reading. We're just reading it in a slightly more efficient way. But yeah, we don't have to allocate slices, and also because we don't have these like nested slices, we don't have like slices that basically have pointers to other slices, so we have better memory locality. And now we're at 46 milliseconds, and that is cool. So 46 milliseconds is basically the time frame that can be acceptable for a database. Okay, so quickly in recap, we immediately ruled out JSON because it just wasn't space efficient, and we knew that we needed something more space efficient and also way faster. Binary encoding already made it much faster, which is great, but if we decode it upfront, then yeah, we still lost a lot of time. And it can be worth it in these kind of high performance situations if you either sort of delay the decoding as late as possible until you really need it, or just don't do it at all, or do it in sort of small parts where we need it. No wish list here, but an honorary mention. So Go 1.20, they've actually removed it from the release notes because it's so experimental. But Go 1.20 has support for memory arenas. And the idea for memory arenas is basically that you can bypass the garbage collector and sort of manually free that data. So if you have something that you know has the same sort of life cycle, then you can say, okay, put it in the arena and basically in the end free the entire arena, which would sort of bypass the garbage collector. So that could also be a solution in this case, if that ever makes it. Like right now it's super experimental and they basically tell you we might just remove it, so don't use it. Third stop is something that when I first heard it almost sounded like too good to be true. So something called SIMD. I'll get to what that is in a second. But first, question to the audience. Who here remembers this thing? Raise your hands. Okay, cool. So you're just as old as I am. So this is the Intel Pentium 2 processor, and this came out in late 90s, I think 1997, and was sold for a couple of years. And back then I did not build databases, definitely not in Go because that also didn't exist yet. But what I would do was sort of try to play 3D video games. And I would urge my parents to get one of those new computers with an Intel Pentium 2 processor. And one of the arguments that I could have used in that discussion was, hey, it comes with MMX technology. And of course I had no idea what that is. And it probably took me 10 or so more years to find out what MMX is. But it's the first in a long list of SIMD instructions. I haven't explained what SIMD is yet, but I will in a second. Some of those, especially the one in the top line, they're not really used anymore these days, but the bottom line, like AVX2 and AVX512, you may have heard them. In fact, for many open source projects, they sometimes just sort of slap that label in the README, like, yeah, has AVX2 optimizations, and that kind of signals you, yeah, we care about speed because it's like low-level optimized. And VVA does the exact same thing, by the way.
Growing a startup is tough. You have limited resources and a lot to do. You're thinking about how to best apply your team's time, maintain infrastructure, or build custom tooling. You're constantly balancing between moving fast and keeping costs under control. Our engineers have kept this top of mind when they designed Google Cloud to be simple to use, so it's faster and easier for you to get things done. Let's break down the 4 key reasons top startups work with us. Number 1 is speed.
So to understand how we could make use of that, I quickly need to talk about vector embeddings, because I said before that VVA doesn't search through data by keywords, but rather through its meaning. And it uses vector embeddings as a tool for that. So this is basically just a long list of numbers, in this case floats. And then a machine learning model comes in and basically it says, do something with my input, and then you get this vector out. And if you do this on all the objects, then you can compare your vectors. So you basically can do a vector similarity comparison, and that tells you if something is close to one another or not. So for example, the query and the object that we had before. So without any SIMD, we can use something called the dot product. The dot product is a simple calculation where basically you multiply each element of the first vector with the same corresponding element of the second vector, and then you just sum up all of those elements. And we can think of this like multiplication and summing as 2 instructions. So if we look out first, shout out here to the compiler explorer, which is a super cool tool to see like what your Go code compiles to. We can see that this indeed turns into 2 instructions. So this is a bit of a lie because there's more stuff going on because it's in a loop, etc. But let's just pretend that indeed we have these 2 instructions to multiply it and to add it. So how could we possibly optimize this even further if we're already at such a low level? Well, we can, because this is our mad journey. So all we have to do is introduce some madness. And what we're doing now is a practice that's called unrolling. So the idea here is that instead of looping over 1 element at a time, we're now looping over 8 elements at a time. But we've gained nothing. Like we're still doing the same kind of work. Like we're doing 16 instructions now in a single loop, and we're just doing fewer iterations. So by this point, nothing gained. But why would we do that? Well, here comes the part where I thought it was too good to be true. What if we could do those 16 operations for the cost of just 2 instructions? Sounds crazy, right? Well, no, because SIMD, I'm finally revealing what the acronym stands for. It stands for single instruction, multiple data. And that is exactly what we're doing here. So we want to do the same thing over and over again, which is multiplication and then additions. And this is exactly what these SIMD instructions provide. So in this case, we can multiply 8 floats with other 8 floats, and then we can add them up. So all is perfect here? Maybe not, because there's a catch, of course. It's our mad journey. How do you tell Go to use these AVX2 instructions? You don't. You write assembly code, because Go has no way to do that directly. The good part is that assembly code integrates really nicely into Go, and in the standard library, it's used over and over again, so it's kind of a standard practice. And there is tooling here, so shout out to Avo, really cool tool that helps you. Basically, you're still writing assembly with Avo, but you're writing it in Go, and then it generates the assembly. So you still need to know what you're doing, but it's like it protects you a bit. So it definitely helped us a lot. So SIMD, recap. Using AVX instructions or other SIMD instructions, you can basically trick your CPU into doing more work for free, but you need to sort of also trick Go to use assembly. And with this tooling such as Avo, it can be better, but it would be even nicer if the language had some sort of support for it. And you might say now, okay, this is this mad guy on stage that wants to build a database, but no one else needs that. But we have this issue here that was opened recently and unfortunately also closed recently because no consensus could be reached. But it comes up back and back basically that Go users are saying like, hey, we want something in the language such as intrinsics. So intrinsics are basically the idea of having high level language instructions to do these sort of AVX or SIMD instructions, and C or C++ has that, for example. One way to do that, and maybe you're wondering like, okay, if you have such a performance hot path, like why don't you just write that in C and use CGO or write it in Rust or something like that? Sounds good in theory, but the problem is that the call overhead to call C or C++ is so high that you actually have to outsource quite a bit of your code for that to pay off again. So if you do that, you basically end up writing more and more and more in that language, and then you're not writing Go anymore. So fortunately, that's not, or it can be in some ways, but it's not always a great idea. So demo time. This was going to be a live demo, and maybe it still is, because I prepared this running nicely in a Docker container, and then my Docker network just broke everything, and it didn't work. But I just rebuilt it without Docker, and I think it might work. If not, I have screenshots basically that do a backup. So example query here. I'm a big wine nerd, so what I did is I put wine reviews into VV8, and I want to search them now. And one way to do it, to show you basically that the keyword that you don't need a keyword match, but can search by meaning is, for example, if I go for an affordable Italian wine. Let's see if the internet connection works. It does. So what we got back is basically this wine review that I wrote about a Barolo that I recently drank. And you can see it doesn't say Italy anywhere. It doesn't say affordable. What it says, like, without breaking the bank. So this is a vector search that basically happened in the background. We can take this one step further by using the generative side. So this is basically the chat GPT part. We can now ask our database, based on the review, which is what I wrote, when is this wine going to be ready to drink? So let's see. You saw before that was the failed query when the internet didn't work. Now it's actually working, so that's nice. And here, in this case, you can see that, so this is using OpenAI, but you can plug in other tools, can plug in open source versions of it. This is using OpenAI because that's nice to be hosted at a service, so I don't have to run the machine learning model on my laptop. Then you can see it tells you the wine is not ready to drink yet. We will need at least 5 more years, which is sort of a good summary of this. And then you can see another wine is ready to drink right now. It's in the perfect drinking window. So for the final demo, let's combine those two. Let's do a semantic search to identify something, and then do an AI generation, basically. So in this case, we're saying, find me an aged classic Riesling, best wine in the world, Riesling. And based on the review, would you consider this wine to be a fruit bomb? So let's have sort of an opinion from the machine learning model in it. And here we got one of my favorite wines. And the model says, no, I would not consider this a fruit bomb. While it does have some fruity notes, it is balanced by the minerality and acidity, which keeps it from being overly sweet or fruity. Which is, if you read the text, like, this is nowhere in there. So this is kind of cool that the model was able to do this. Okay, so let's go back. Now is the demo time. By the way, I have a GitHub repo with like this example, so you can run it yourself and try it out yourself. So this was our mad journey, and are we mad at Go? Are we mad to do this? Well, I would pretty much say no, because yes, there were a couple of parts where we had to get really creative and had to do some rather unique stuff. But that was also basically like the highlight reel of building a database. And all the other parts, like, it didn't even show the parts that went great, like concurrency handling and the powerful standard library. And of course, all of you, basically, representing the Gopher community, which is super helpful. And yeah, this was my way to basically give back to all of you. So if you ever want to build a database or run into other kind of high performance problems, then maybe some of those examples helped you. And if you now want to try out Veviate, you can see it on Veviate.io, or the GitHub is Veviate/Veviate. You can follow me on Twitter at EtienneDI, or you can follow Veviate at Veviate.io. I don't have a Mastodon yet, because that kind of seems to be the new thing, but I was busy writing assembly code, so I had no time to create one yet. Yeah, that is our mad journey. Thank you very much.
Can I have one applause?
Cool. If you have...
Yeah, I see a question. I'll try to run towards you. I've been running all day, so it might be slow.
Hi, thank you for your talk. Quick question about compression. You talked a lot about data size. Have you weighted the pros and cons between compression to reduce the size, and so the bandwidth needed to read the data, and then
Yes.
the penalty of decompressing?
Yes, absolutely. So basically, the uncompressed example was sort of the simplified version, because 25-minute talk and had to cut down. In real life, definitely compression, especially like using a uint64 in this example, most of the bits are probably going to be 0, so you can gain a lot from compression. And we have an inverted index also in Veviate. So we have these like kind of posting lists, and they're very similar because they start from 0 basically and go up. So there's lots of overlap and lots of gains to be made with compression. Yeah, maybe something for our mad journey part 2.
Yeah, so my first question is, doesn't Go itself leverage these SIMD things? It seems like compiler should do these things.
Yes, it does, and it does so sort of okay-ish. The problem is basically, typically with like the AVX 512, where we wanted to do 8 things at once, this is specific to some CPUs, and then the Go compiler doesn't do it as well. Typically, from the way that the Go compiler does it, I could get like a 2 times speed up, but never more, sort of never in the sort of realms of 8 times. But in general, and this is not so much a Go-specific thing, like hand-optimized assembly or low-level SIMD is most likely going to be faster than what a compiler do, simply for the fact that you know exactly what you want to do, like how long is the data going to be, this kind of stuff, whereas the compiler basically has to guess.
And the second question is like, did you try any other encoding, like something like there was something called group variant. I'm not sure we are using floats here, but there are other encoding algorithms which might save the space more, like.
Yeah, this goes in the same direction basically as the compression question. So definitely more, this is sort of a, I don't want to say a fictional example, but it's sort of a simplified example for the purpose of a slide.
Okay, one round. Sorry, we're running out of time. You can ask in the hallway track.
Good morning. Wow, I was not expecting this much of an audience at 9 a.m. on Sunday at a FOSDEM, so thank you all for coming. Yeah, I'm here to talk about how I was at FOSDEM 5 years ago. I told you all a whole bunch of things, and I was utterly wrong so many ways. It's actually kind of amusing. But who am I?
Okay, sorry. I guess you didn't hear anything I just said. I was just talking to somebody, my business partner, about the Shopify site, and or one of my business partners, and trying to have conversations about some stuff at the same time. And I got to put this Bloom stuff in somewhere. Now the code was for some reason wasn't inside the app directory where it should have been. I think it should have been an app directory. What am I missing? Oh, I'm in the wrong studio. Like an idiot. Right. I'm supposed to be in this one. Okay. Let me close down this other one that's confusing me. I'm distracted. Okay, leave that alone. Let's just do it from here. And here, share this tab. Okay, so we have to enter in, we have to get the secret, and you guys can't see what that is. So I gotta share this tab instead. Find the client equals this code, which should be in here. I'm just gonna go back. How am I supposed to? Oh, it turned off. Okay, it turned back to this tab. It turned off for after 10 minutes, so I have to turn back on. Okay. All right, stay focused. Okay, so this I have to update the URL, and there it is. The API key. So you can't see this. Let's see. So I'm going to share this tab instead. The API key and then URL. Where's the API key? Dashboard. API keys. Sandbox. There's supposed to be a min scope. Maybe. And public. Okay, so there's two of them. All right, there's min and public. I want the public one, right? No. Okay, I just want the min one. Scope is min. In order to get the scope, in order to do that, you have to go here to computers and switch environment. I'm going to change that, but it's not just so easy just changing for because I go new and then fill it in. Stop sharing video for a minute. And do something else like emails. Come on. Think. Do this. Okay. Think. The API key is the URL. It's just the URL. Okay, so I don't want to share that code. I want to share just this part. Okay, so I stay there. URL. Let me see if this will work. Come on. It's a card. Um, where did you put it? I hate it when it's that. It's just like random. Index as query engine. Index as query engine. Index as query engine. Index name equals. Index equals setup index. Vector store client equals blah blah, client equals blah blah, and then vector store equals vector store mark external context. Index name equals my external context. Yeah, storage context now. Both context equals blah blah. Okay, looks alright. Okay, pip. Doesn't have any requirements for it. Hi, how's it going? I'm here. Can you hear me now? Yes, good. Let me just plug in my headphones so I can hear you better. I'm live streaming, so I'm going to change the stream to something else so while we have a little chat here. So I'm live streaming with Daniel, or talking with Daniel right now, and so I'm going to stop the live stream temporarily and play a video for you guys to watch.
LangGraph. You can think of this as sort of the new way to run agents with LangChain. So it's fully compatible with the LangChain ecosystem, and especially can really make good use of the new sort of custom chains with the LangChain expression language. But this is built for running agents. So they talk about the idea of being a graph, and what they're talking about, a graph here is where you've basically got nodes joining to different edges, and they're not always going to be directed. So this is not a DAG or a fixed directed graph in any way. This is basically where nodes can make decisions about which node they can go to next. So another way of thinking about this is it's like a giant state machine that you're building, where the graph is basically the state machine that decides, okay, what state are you in now? What state will you go to run a particular chain or to run a particular tool, etc.? And then how do you get back? And then also things like, how do you know when to complete or end the graph or end the sequence in here? So LangGraph is built on these ideas of trying to make it easier for you to build custom agents and to build things that are more than just simple chains with LangChain. So there are a number of key parts to this. You've got this idea of a state graph. So this is where your state is being persisted in some way throughout the agent's lifecycle. And you can think about this as a sort of way of passing the dictionary around from chain to chain or from chain to tool and stuff like that, and then being able to update certain things. And you can update things where you can just overwrite them or you can add to them. So if you've got a list of things like immediate steps, you can basically add to that as the agent is actually going through running the various parts of the graph, etc. The next part, which is key to this, is the whole idea of nodes. as you build the graph, you want to add nodes to the graph. And you can think of these nodes as being like chains, or actually they're also runnables. So it could be a tool, it could be a chain, and you could have a variety of these different nodes. And you think of those as being like the components of your agent that you need to wire together somehow. So while the nodes are the actual component, the edges are what wires everything together. And the edges can come in different forms as well. So you can set an edge where it's just going to always go from this node to this other node. So if you have a return from a tool going back to the main node, you're just going to let that, you're going to want to probably hardwire that in there. But you can also then set edges which are conditional edges. And these conditional edges allow a function, often going to be the LLM, to actually decide which node that you go to next. So you can imagine that this can be useful for deciding if you're going to go to a tool, what tool you're going to go to. If you're going to go to a different sort of persona in the agent, let's say your agent has got multiple personas and you want to go from one to the other, or you want to have a supervisor that's basically delegating to different personas, all those things are going to be on sort of conditional edges that we go through. Now, once we've set up these nodes and we've set up these conditional edges, you then basically want to compile the graph. And now the graph acts just like a sort of standard LangChain runnable. So you can run invoke on it, you can run stream, etc. It will now basically run the state of the agent for you and give you the entry point. You will define an entry point as an entry node and give you the sort of endpoint. And it will be able to get through the whole sort of thing of wiring these things together. Now, I can see that there's going to be a lot of use for sort of making reusable sort of agents that you would then wire together on a graph. So you might have lots of little pre-made things for using tools, that kind of thing. And you could imagine also that you've got agents that use certain kinds of prompts based on the inputs that come before them here. What I want to do now is go through some of the code. We'll look at some of the examples that they've given. I've gone through and changed them a bit just to highlight what's going on. And then we'll also look at it in Langsmith so we can actually sort of see what actually happens at each step and what gets sent out to the large language model, etc. You'll find that I'm using the OpenAI models in here. There's no reason why we can't use other models. The only, I guess, challenge is that a lot of those models need to support function calling if you're going to be using function calling on these. Now, if you're just running sort of standard chains or something where you're not using the function calling, you could use any sort of model. But if you want to have the parts where you're using function calling to make the decisions and stuff, then you're probably looking at models like the OpenAI models, like the Gemini models. And now we're starting to see some open source models that can do this function calling stuff as well. All right, let's jump in and have a look at the code. All right, let's start off with the simplest sort of example they give, which is probably not that simple in some ways. The agent executor. So this has been around in LangChain for quite a while. You can think of it as a way of building an agent where you can then use function calling to get a bunch of responses in here. So what I've done is I've taken their notebook, I've sort of changed it a bit. I'm going to make some things a little bit simpler, and I'm going to add some more things to it so we can sort of get a sense of, okay, what actually is going on in here. So first off is basically setting the state. So I've left a lot of their comments in here. There are a number of key things that you want to persist across the actual agent while it's running. So in this case, they're persisting the input, they're persisting a chat history. So this is more a sort of traditional way of adding the memory and doing that kind of thing. You'll see in the second notebook that we move to more just a list of messages going back. But this is using more of sort of a traditional way of having a chat history and then having things like intermediate steps here. And you'll see that some of these things can be basically overwritten. So this agent outcome gives us the outcome from something that the agent did, or gives us this agent finish of when the actual agent should finish. So in this case, this can be overwritten as a value in here. Whereas things like the intermediate steps here, this is basically a list of steps of agent outcomes or agent actions rather, and then sort of the results of those actions. And you can see in this case, this is being operated.add. So this is just adding to the list as we go through it. So this state that you start out with, we're going to pass that in to make the graph later on. All right. Now, what I wanted to do is set up some custom tools in here. Many of you have seen custom tools before. I did some videos about it a long time back. I probably should have done some more videos updating as things in LangChain for it. But if you think custom tools, you can basically pick a bunch of pre-made tools from LangChain, and there are a lot of those already. But you can also do custom tools. So here I've made two sort of silly little custom tools. And one is basically just going to give us a random number between 0 and 100. And the other one's just going to take the input of whatever we've got and turn it into lowercase, right? So these are very simple functions. You can see here we're using the tool decorator to basically convert these into tools. And then when we do that, we're getting the name of the tool, we're getting the description of the tool in this way. So it's a nice way of just quickly making tools in here. And you can see that when I want to run these tools, I basically just say whatever the tool is or the function, and then basically just .run. In the case of random, I'm having to pass something in. So I'm just passing in a string. Really, the string can be anything in here. It doesn't really matter. You'll see that the agent likes to pass in random. So I've given this as an example here, but really it could be an empty string. It could be a string with whatever in it. So in this case, the input is not that important. In this case, the input is important. In this case, we're basically, if I pass something in uppercase, it will be converted to lowercase, right? So whatever the string gets passed in, that will be converted to lowercase and then passed back out. Now, they're simple tools. You could change with this with a bunch of different things like search, DuckDuckGo. Tavili is what they originally used in here. But I kind of feel these are nice, simple tools where you can go in and then see very clearly what is it that's going on, is, what I think going on, rather than getting this long JSON back of a search or something like that. All right, next up, we've basically got the way of making an agent. Now, remember, a graph can have multiple agents. It can have multiple parts of agents, can have multiple chains in there. In this case, this is the sort of agent, the standard sort of agent, which basically uses OpenAI functions, right? You can think of it as an OpenAI functions agent here. So here we're basically pulling in a prompt. This is what they had originally where they were pulling in the prompt from the hub. If we go and have a look at that prompt, we can see that there's really nothing special in there, right? It's basically just got a system message saying you are a helpful assistant. It's going to have a placeholder for chat history. It's going to have a human message, which is going to be the input. It's going to have a placeholder for the agent scratchpad in there. So that's what we're getting back from that when we just pull that down from the hub. We set up our LLM. And then we've got this create open functions agent, which is going to be an agent runnable in here. So I passed in the LLM, the tools, the prompt that we're getting back here. And then you can see that if we actually look at the prompt, it looks quite complicated because it's got a bunch of different parts going on in there. And we can look at the prompt two ways. We can just look at it like this. We can actually get prompts and stuff like that. And you'll see that now if I've got that agent, I can just pass an input into it. And I need to pass in a dictionary, right? So I've got a dictionary with my input text, I've got a chat history, I've got intermediate steps. Neither of those have got anything in here. All right, so we've got these inputs. We pass this in, and you can see that the outcome that we're getting from this is that we're getting an agent action message log response back. So this is basically telling us, give me a random number and then write in words to make it lowercase. So you can see that, all right, what's it doing? It's basically deciding what tool to select via a function call. So if we come in here and look at Langsmith, we can see that when we actually passed this into the LLM, we were passing in these functions and tools in here as well, right? So we can see that this has got the details for that tool. We've got the details for the random number tool, and they've been converted to the OpenAI functions format for us in there. We then basically have got our input, our system input, and then we've got the human input there. And we can see the output that came back was this function call saying that we need to call random number. And if we look back here, we can see that, okay, it's actually passing back that we're going to call random number with the input being random. And we've got a message log back there as well. All right, so this was basically one step in the agent. So this hasn't called the tool for us. It's just told us what tool to actually call in here. So that's showing you what that initial part does. Now we're going to use that as a node on our graph. And we're going to be able to go back and forth to that between that particular node and the tools node as we go through this. First off, we want to set up the ability to execute the tools. So we've got this tools executor here. We pass in the list of tools that we had. So remember, we've got two tools, one being a random number generator and one being convert things to lowercase. If we come up here and we look at, okay, the first thing we're going to do, what are we going to put on this graph? We're going to put in the agent, but we're actually going to run the agent. So we've got that agent runnable, invoke, and then the data that we're going to pass in. And you can see that we return back the agent outcome from that. So in this first case, that agent outcome is going to be telling it what tool to use. If we put the same inputs that we had before there. We've then got a second function for actually running the tools. So you can see here that this is going to basically get this agent outcome. That's going to be our agent action, which is going to be what tool to run, etc. And then we can run this tool executor function and just invoke this with the telling it what tool and what input to pass in there. Now I've added some print functions in here just so that we can look at, okay, the agent action is what actually it is, and also then the output that we get back from that. Finally, when we get that output back, we add that to the intermediate steps there. The next function we've got is for dealing with, okay, do we now, so remember that each of these can be called at different stages, even though I'm going through the agent tools, stuff like that. These are separate things at the moment. The next thing that we've got, this function, is basically determining, okay, based on the last agent outcome, do we end or do we continue? If it's going to be like an agent finish, then we're going to end, right? We're not going to be doing something. So if it's coming back where it's saying, giving us the final answer out, we don't need to go and call tools again. We don't need to call another language model call again. We just finish there. So these functions you're going to see are what we're going to add in here. So first off, we've got our workflow, which is going to be the state graph, and we're passing in that agent state that we defined earlier on. We're then going to add a node for agent, and that's going to be running the agent there. We're going to add a node for action, and we could have called this actually tools, right? Tool action or something like that. This is going to be the function that we've got here for actually running the tool and getting the response back and sticking it back on immediate steps like that. All right, so they're the two main nodes that we've got there. We set the entry node in here. So we've got this entry node. We're going to start with agent because we're going to take the inputs. We're going to run that straight in, just like we did above there. And then you can see, okay, now we need to basically put in the conditional edges. The conditional edges is where we're using this function should continue. And we're basically saying that after agent, the conditional edges are going to be, okay, should we continue or not? You'll see down here, I'll come back to this in a second, but you'll see down here, we've got a sort of a fixed edge where we always go from action back to agent. So meaning that we take the output of the tool and we use that as the input for calling the agent again. But then the agent can then decide, okay, do I need to use another tool or can I just finish here? And that's what this conditional edge is. So after the agent, it will decide if I ask it something that's totally not using any of those tools, it's just going to give me a normal answer back from a large language model or from the OpenAI language model in here. But if I give it something where it's going to be an action, then it's going to continue and it's going to go on to use the tools and stuff in there. So here we want to sort of decide, this is this sort of conditional edge part. And you'll see this in one of the other notebooks that this can get a lot more complicated if you've got multiple agents going on the same graph as we go through this. All right, we then compile the graph. I've tried to go with the terminology as much as they've got here of like workflow and stuff like that. But really, this is the graph. We're compiling it to be like an app in here. If we look at it, we can actually see the branches that are going on. If we look at it, we can also see the nodes that are on this and the edges that are on this. So we can see, okay, what goes from what. And we can also see the intermediate steps of how they're being persisted on that graph. Okay, so now we're going to basically stream the response out so we can see this going through. I'm basically just going to take this app. Remember, I can do .invoke, I can do .stream, and I'm going to pass in the inputs. Inputs here are going to have an empty chat history, but I'm going to pass in the input basically saying, give me a random number and then write in words, should be write it in words, but anyway, write it in words and make it lowercase. So you'll see that, all right, what happens here? So we start off and it decides, okay, I need a tool, right? So its tool is going to be random number. And in this case, it's putting the input being random number. It then gets that response back. Now I've printed this, so that it then basically sends that to the tool, right? So you see each of these is where we're going from one node to the next node that we're printing out here. So we go from this agent run node, the outcome being that, okay, I need to run a tool, coming back. And then in this one, we're going to basically now have it where we've run the tool. It's given us back a random number. The random number is 4 in this case. And so now it's going to stick that on the intermediate steps in there. So now that's going to be passed back to our original agent node. And now it basically says, okay, this was my initial sort of thing. I've got this number back. Oh, I need to write it in words. And then I need to make it lowercase. So to make it lowercase, I need to use a tool. And the tool is lowercase in this case, right? So the input is going to be 4 with all capitals. And you'll see that the lowercase that we're getting out here is going to return back somewhere here. We'll see this. It's going to return back. Yes, here we're going to see the tool result is 4 in lowercase there. So again, this is a tool. This is the straight up agent. This is the tool. This is the initial agent again. This is the tool. And then finally we go back to the agent again. And now it says, okay, now I can do agent finish. Because I've done everything that I was asked to do in there. I've got the random number. I've got it in words. I've got it in lowercase here. So we can see that the output here is the random number is 4. And when written in words and converted to lowercase, it is 4, right? So it's a bit of a silly sort of task to do it, but it shows you how it's breaking it down. And we can see if we look at the intermediate steps that we're getting out there, we've got the steps for each of the different things going along. We've got the message log and stuff as we're going through this. All right, if we wanted to do it without streaming it, we could do it like this. If I just say invoke, I'm not going to see each agent broken out. I'm just going to see, okay, that first off, it's going to pick the random number tool, gets 60, takes that as a word in uppercase, puts it into the lowercase tool, and we get the result in here. Now, I've saved the output to output in this case. So remember, these are print statements that I put in there. That's why we're seeing this come along. And then we've got this agent, get agent outcome. If we return values and get the output, we can see the random number is 60. And in words, it is 60, all in lowercase. If we want to see the intermediate steps, we can see the intermediate steps there. Just to show you, sort of finish off, if we didn't put something in that needed a tool, if we just put in the, okay, does it get cold in San Francisco in January? It comes back, yes, San Francisco can experience cold weather in January. So now notice it didn't use any tools. It just came straight back with a finish and there's no intermediate steps, right? We've just got that one call going on in here. So if we come in here and have a look in Langsmith, we can see this going on. So we could see that, okay, we started out with that call. It basically gave us a return to recall the random number. We got random number. We got 4 out of that. From that, we then basically went back. So that, remember, the action is like our tools. We went back to the agent and we can see that if we look at the OpenAI thing here, we can actually see what was getting passed in here. And we can see that, okay, it's going to come back that the input is 4 in capital letters. We'll go into the tool lowercase. Yeah, this is going to transform it to just deliver back 4 in lowercase. And then finally, we're going to pass that in. If we look at here, we're passing all of that in with the string of, okay, what we've actually done in here as well. And now it can say, okay, the output is going to be, the random number is 4. And when written in words, it's converted to lowercase 4, right? And you can see the type that we got back was agent finish. So that's what tells it not to continue as we go through this. All right, let's jump in and have a look at the second example. So the second example in here is very similar. The big difference here is it's using a chat model and it's using a list of messages rather than this sort of chat history that we had before. So we've got the tools here. Now, one of the things with doing it this way is that we're not using the create OpenAI functions agent here. So we are using an OpenAI model, but we need to basically bind the functions to the model. So we've got the model up here and we can basically just bind these. So we just go through for each tool that we've got in here, We run it through this format tool to OpenAI functions format, and then we basically bind that to the model. So meaning that the model can then use that and call back a function just like it did before in there. All right, we've got an agent state again, like we had before. This is the sort of state graph that we had here. In this case, the only thing that we're going to have, though, is just messages. We don't need to have the intermediate steps. We're not doing any of that stuff. And because the input is already in the messages, we can actually get at that here. So we don't need to persist that either. All right, our nodes. So we've got the should continue node again. So this again is going to decide whether we go back to the sort of original agent node or whether we go to the tools node. And in this case, you can see that what it's actually doing is it's getting off that the last message that we got back, and it's using that to basically see, is there a function call in that or not? If it doesn't have a function call, we know then that's not using a tool, so we can just end. If it does, we can then continue. We've then got basically calling the model. So this is taking our messages, passing this in and invoking the model. We're going to get back a response for that. So we've got this response and we're just putting that response back in there. We've got a function for calling the tool. Okay, here again, we're going to get the last message because this is what's going to have the actual function that we need to call or the tool that we need to call. So you can see that we get that by just getting last message, looking at function call, getting the name, and then that basically passes that back of what the tool is. And then same kind of thing for getting the tool input in here. And then here I'm just basically printing out that agent action is that action again, so we can actually see what's going on and the response back, the same as what we did in the previous one. And then we're going to basically use that response to create a function message, which we can then basically assign to the list of messages. So it can be the last message that gets taken off and passed back into the agent again. All right, we've got the graph here, same kind of thing. We add two nodes. We've got one node being the initial sort of agent and one node being the tool or the action that gets called. Here we set the entry point to agent again. We've got our conditional, the same as we had before as we go through this. So we've got a conditional edge and we've also got a hardwired edge, being that always from action, we always go back to agent in this case. Compile it, and then now we can just run it. So you can see here that we can, I'm just going to invoke these as we go through it. We can see that I've got, give me a random number and then write the words and make it lowercase. We can see we're getting the same thing as what we had before. So this is replicating the same kind of functionality, but you're going to find that in some ways this allows you to do a lot more things in here, in that if we were to come in here, you see how we're popping off the last message when we come in here. We're also able to basically summarize messages. We're able to play with the messages. We're able to limit it so that we've only got the last 10 messages in memory so that we're not making our calls 35 messages long or something like that. Even with the GPT-4 Turbo, we can go really long, but we don't probably want to waste so much money by doing really long calls and using up really large amounts of tokens in the context window there. So we can run that through. You can see here, we've asked for the random number. Sure enough, it's done the same thing. It's got the tool. And remember, these are coming from the print statements that I put in there. And we're then basically getting this output in here. So that's the output of the whole thing that's coming back with the various messages that we've got going through. And those messages, everything from the system message to human message to the AI message to a function message to an AI message again to a function message back to an AI message for the final one out there. If we just want to try where it's just using one tool, so here I've put in, please write Merline in lowercase. You can see now it just uses one tool, just uses the lowercase one, goes through and does that. And then again, if we want to just try it with no tools, if I ask it, okay, what is a merline? A merline is a mythical creature with a head of a lion and a body of a fish. All right. So this sort of shows you that it can handle both using the tools and not using the tools. And it also shows you that each time, though, we're getting these list of messages back, which is the way of us being able to see what's going on and persist the conversation as we go through this. Okay, in this third notebook, we're going to look at the idea of building a sort of agent supervisor. So where you've got it so that the user is going to pass something in, the supervisor is then going to decide, okay, which agent do I actually route this to? And then it's going to get the responses back. And some of these agents can be tools. Some of them can be just other agents that actually are not using a tool, but are using a large language model, etc. So let's jump in. So we've got the same imports that we had before. I'm setting up Langsmith in here. I'm bringing in the model. So the model I'm going to use for this one is GPT-4. And then we've got a number of tools in here. I've got my custom tools that we've used in the first two notebooks. So the lowercase and the random number there. But we've also got the Python REPL tool, right? Remember, there's a read, evaluate, print loop tool. So basically you can run Python code. So you always want to be a bit careful of what prompts you're letting go into that, because it can be used maliciously. Obviously, if it can run anything that Python can run, it can do a lot of damage in there. All right, so then in the example notebook, they've got these helper utilities. This is basically for making a general agent. And you can see that we're going to pass in the LLM. We're going to pass in the tools that the agent can use. We're going to pass in a system prompt for this. And it will then basically assemble it with the messages, with the scratch pad, etc. And it's going to make that create OpenAI tools agent, just like we had in the first notebook that we went through. And it's going to then return that executor back. Yeah. So this is just a way to sort of instantiate multiple agents based on their prompts and stuff like that. So the second helper function here is basically this agent node, which is for converting what we got here, creating the agent into an actual agent node so that it can be run in here. It's also got a thing where it's going to take the message and convert it to being a human message. Because we've got multiple agents, which are going to be LLM responses and stuff, we're often going to want to convert those to be human responses to get the sequence of responses as we go through this. All right, next up is creating the agent supervisor. So this case is where you're going to determine your multiple agent personalities and stuff like that. So the personas I've got here, I've changed their example. So I've got the lotto manager, which is obviously going to use the tools that we had before of the random number, etc. And we've got a coder. So I've stuck to the original example that they had of having a coder that will make a plot out of this. But what we're going to do is plot out the lotto numbers for this. So we can see here that this supervisor has got a very sort of unique prompt, right? It's basically that you're a supervisor tasked with managing conversation between the following workers. And then we're passing in that members. So the members is this lotto manager and coder. Given the following user request, respond with the worker to act next. So each worker will perform a task and respond with their results and status. When finished, respond with finish. So this is what's guiding the supervisor to decide the delegation and to basically decide when it should finish for these. So for doing that delegation, it's going to use an OpenAI function. And this is basically setting this up. So this is setting up like the router for deciding the next role of who should do it, and then passing these things through and passing in like this enum of the members and finish. So it can decide, do I finish? Do I go to this member? Do I go to this other member as we go through this? And you can see that because that is its own call in here, we've got a system prompt there that says, given the conversation above, who should act next? And then we basically give it the options of finish, lotto manager, or coder in this. And then basically just putting these things together, making this supervisor chain where we're going to have this prompt. We're going to bind these functions, this function above that we've just had to the LLM, and then we're going to pass that out, getting that back. So hopefully it's obvious that will then become like a node on the actual graph as well. So now we're going to look at actually creating the graph. So we've got this agent state going on here. And so this is our graph state. Again, we're going to have the messages that we're going to be passing it in. So we're sticking to the sort of chat executor like we did in the second notebook there. And you can see here that we're going to basically have the lotto agent. So I'm just going to instantiate these with that helper function for create agent. And so here I've got a lotto agent. It's going to take in our GPT-4 turbo model. It's going to take in the tools. And then the prompt for this is you are a senior lotto manager. You run the lotto and get random numbers, right? It's telling it that, hey, this is the agent to do that. It's then going to have to basically use the tools to do that. So that's the Lotto agent. And then the second agent is this coda agent. So this coda agent is just using the tools. So I passed in all the tools in here for tools, by the way. And this particular agent is just going to use the Python REPL tool. And this is basically saying you may generate safe Python code to analyze data and generate charts using matplotlib. So it's just setting it up to do the charting in there. So if you look carefully, you'll actually see that I think I accidentally passed in the Python REPL into these tools as well. So it's not ideal in that we would want to limit the number of tools that we pass into something to as few as possible. One, it saves on tokens, and two, it just makes it easier for the model to make the decision. But anyway, we've got those, and then we've got this basically setting up the node here. And so we've got our Lotto node, we've got our code node. We can then basically pass these in as we go through this. We need some edges. So the edges, we've actually got a lot more edges because we've got a lot more nodes now. And you can see that they're just using a for loop to make these edges. So from every agent or persona, whether it's the Lotto manager, whether it's the coder, it always goes back to the supervisor. So even if we had 10 different agents, you can see here we've got 2 being Lotto manager and coder, it will go back to the supervisor at the end of that. And then we've got conditional ones where it will just determine, this is sort of setting up a conditional map for the conditional edge of being the supervisor going to what. So this conditional map, in fact, maybe in a future example, I will just hard code this out so people can sort of see what's going on here. But basically, it's just making a dictionary in here. It's adding in the finish node in there as well that it can basically use as a condition. And we can see that we can go from supervisor to any of those on the conditional map, which is going to be our members, and it's going to be finish in there. Finally, we set up the entry point. So the entry point is going to be the supervisor, compile our graph, and then we can use the graph. So you can see now what I've asked it to do is human message in, get 10 random Lotto numbers and plot them on a histogram in 10 bins and tell me what the 10 numbers are at the end. So this runs through, it does the plot for us. So we don't really see that much here, but let's jump over to Langsmith and see what's going on here. If we look at the Langsmith for this, we can see that it starts out and we've got the router as the actual function calling thing at the start, right? Not the tools. This is the router that is basically deciding, do I go to Lotto Manager? Do I go to Coda? Do I go to finish off this? We pass in our prompt there, and you can see now it's got the workers being Lotto Manager and Coda, which got put in there. And then we've got when finished, respond with finish. And then we passed in the actual sort of human prompt. And you can see that it's decided that, okay, from this, select one of these. It's decided, okay, I need to go to Lotto Manager. So that's where we get to Lotto Manager. Now, Lotto Manager basically looks at this, and now it's getting tools in there. So remember I said I accidentally passed in the Python REPL in here. I probably shouldn't have done that. But anyway, we've got your senior Lotto Manager, get 10 random Lotto numbers. We're passing in that in there. And you can see it's worked out that, okay, it needs to do this random thing, and it needs to do it 10 times. So it goes through and runs the random number tool 10 times. So we get 10 separate random numbers back from that. It then can take those and decide, okay, there's our 10 numbers back that we got. And it can decide, okay, now it needs to go to the coder. Now, in this case, actually, because it had the Python REPL in here, it just did it itself in here. But you'll see on some of them, it will actually go back to the coder in there. And then finally, we've got the supervisor out, which is giving the Lotto numbers out, telling us that we can't see the plot. You can't pass the plot back because it's already plotted it out. Here is our plot out. And if we went along, we can see that here are the numbers that correspond to the plot out that we've got there. Anyway, this is just running it 2 times. If we look at the final response out, we can see that this is what we've got. If we want to actually just sort of give the human response back out, we can get this out. So we've got this histogram has been plotted for the following numbers, passing in the numbers with new line characters, etc., as we go through it. Okay, so this shows you the sort of basics of building a supervisor agent that can direct multiple agents in here. So in some future videos, I think we'll look at how to actually go through this more in depth and actually do some more real world agent things with this. And then from this, you could basically take it, you could deploy it with a LangServe, you could do a variety of different things with it to make a nice UI or something for this. But hopefully this gives you a sort of crash course in what LangGraph actually does and what some of the key components are for it. If you just think of it as being a state machine, this is fundamentally how I think about it. If you've ever done any sort of programming for games and stuff, you often use state machines there. A lot of sort of coding will often have some kind of state machine. And the state machine is basically just directing things around this. So don't be intimidated by it. It's pretty powerful that you can do a lot of different stuff. I would say it can get confusing at times when you're first getting your head around it. But once you sort of work out like how you're setting up the different nodes, what the actual nodes are, how you're going to have conditional edges between the nodes, and then what should be hardwired edges to basically bring things back is another way of thinking through this. So for me, I'm really curious to see what kind of agents people want to learn to actually build. Agents are something that I've been interested in with LangChain for over a year or so. And I'm really curious to see, okay, what kind of agents do you want? And we can make some different examples of these. In the description, I'm going to put a Google form of just basically asking you a little bit about what agents you're interested to see and stuff like that. If you are interested to find out more about this, fill out the form, and then that will help work out what things to go with going forward. Anyway, as always, if you've got comments, put them in the comments below. I always try to read the comments for the first 24 hours or 48 hours after the video is published and reply to people. So if you do have any questions, put them in there. And as always, I will see you in the next video. Bye.
That grimy film on your teeth.
Dr. G?
It's actually the buildup of plaque bacteria, which can cause cavities.
Unlike other toothpastes, Crest Pro Health's antibacterial fluoride fights bacteria for 12 hours.
It stops cavities before they start.
Crest.
So you're talking about the symmetries in data. Could these analogies also be represented using the kind of symmetries that you're talking about?
Good question. What do you think of it a bit?
Modern machine learning operates with large, high-quality data sets, which together with appropriate computational resources motivates the design of rich function spaces with the capacity to interpolate over the data points. Now, this mindset plays well with neural networks, since even the simplest choices of inductive prior yield a dense class of functions. Now, symmetry, as wide or narrow as you may define its meaning, is one idea by which man, through the ages, has tried to comprehend and create order, beauty, and perfection. And that was a quote from Hermann Weyl, a German mathematician who was born in the 19th century. Now, since the early days, researchers have adapted neural networks to exploit the low-dimensional geometry arising from physical measurements. For example, grids in images, sequences in time series, or position and momentum in molecules and their associated symmetries, such as translation or rotation. Now, folks, this is an epic special edition of MLST. We've been working on this since May of this year, so please use the table of contents on YouTube if you want to skip around. The show is about 3.5 hours long. The second half of the show, roughly speaking, is a traditional style MLST episode, but the beginning part is a bit of an experiment for us, maybe a bit of a departure. We want to make some Netflix style content, and we've even been filming on location with our guests. So I hope you enjoy the show and let us know what you think in the YouTube comments. Many people intuit that there are some deep theoretical links between some of the recent deep learning model architectures, particularly the ones on sets actually. And this may be why so many popular architectures keep getting reinvented. Now, the other day, Fabian Fuchs from Oxford University released a really cool blog post about deep learning on sets, elucidating a math-heavy paper that he co-authored with Edward Wagstaff et al. Now, he wanted to understand why so many neural network architectures for sets resemble either deep sets or self-attention. Because sets come in any ordering. There are many opportunities to design inductive priors to capture the symmetries. So it raises the question, how do we design deep learning algorithms that are invariant to semantically equivalent transformations while maintaining maximum expressivity? Now, Fabian pointed out that the so-called Genossi pooling framework gives a satisfying explanation. Genossi pooling is when you generate all of the k-tuples of a set and average over your target function on those permutations. It gives you a computationally tractable way of achieving permutation invariance. So rather than computing n factorial combinations of the examples, you compute n factorial divided by n minus k factorial, which for small k is very tractable. Now clearly, setting k to n gives you the most expressive, yet the most expensive model. But that would be cool. It would model the high order interactions between the examples. But it turns out that deep sets are this configuration with k equals 1, and self-attention is this configuration with k equals 2. Now Fabian also spoke about approximate permutation invariance, which is when you set k to n, the number of examples, but you sample the permutations. Turns out you don't have to sample very many of them to get good results. But anyway, if you want to check out that in a little bit more detail, go and check out Fabian's blog. I've put a link in the video description. High dimensional learning is impossible due to the curse of dimensionality. It only works if we make some very strong assumptions about the regularities of the space of functions that we need to search through. Now, the classical assumptions that we make in machine learning are no longer relevant. Now, in general, learning in high dimensions is intractable. The number of samples grows exponentially with the number of dimensions. The universal function approximation theorem, popularized in the 1990s, states that for the class of shallow neural network functions, you can approximate any continuous function to arbitrary precision by just stacking the neurons, right? Assuming that you had enough of them. So it's a bit like kind of sparse coding, if you like. The curse of dimensionality refers to the various phenomena that arise when analyzing and organizing data in high-dimensional spaces that do not occur in low-dimensional settings, such as the three-dimensional physical space of everyday experience. Now, the common theme of these problems is that when the dimensionality increases, the volume of the space increases so fast that the available data effectively becomes sparse. This sparsity is problematic for any method that requires statistical significance. Now, in order to obtain a statistically sound and reliable result, the amount of data needed to support the result often grows exponentially with the dimensionality. Most of the information in data has regularities. Now, what this means in plain English is just like on a kaleidoscope, most of the information which has been generated by the physical world is actually redundant, just many repeated semantically equivalent replicas of the same thing. The world is full of simulacrums. Machine learning algorithms need to encode the appropriate notion of regularity to cut down the search space of possible functions. You might have heard this idea referred to as an inductive bias. Now, machine learning is about trading off these three sources of error. Statistical error from approximating the expectations on a finite sample, and this grows as you increase your hypothesis space. Approximation error, which is how good is your model in that hypothesis space. If your function space is too small, then the one that you find will incur a lot of approximation error. And finally, optimization error, which is the ability to find a global optimum. Now, even if we make strong assumptions about our hypothesis space, which is to say that it should be Lipschitz, or in plain English, it should be locally smooth, it's still way too large. We want to have a way to search through this space to get anywhere. So the statistical error is cursed by the dimensionality. If we make the hypothesis or the function space really small, then the search space is smaller, but the approximation error is cursed by dimensionality. So we need to define better function spaces to search through. But how? We need to move towards a new class of function spaces, which is to say, geometrically inspired function spaces. Let's exploit the underlying low-dimensional structure of the high-dimensional input space. The geometric domain can give us entirely new notions of regularity, which we can exploit. Now, using geometrical priors, which is to say only allowing equivariant functions or ones which respect a particular geometrical principle, this will reduce the space of possible functions that we search through, which means less risk of statistical error and less risk of overfitting. We should be able to do this without increasing approximation error, because we should know for sure that the true function has a certain geometrical property which will bias into the model. So, introducing the geometrical deep learning proto book. So recently, Professor Michael Bronstein, Professor Joanne Brunner, Dr. Taco Cohen, and Dr. Petar Velichkovic released an epic proto book called Geometric Deep Learning, Grids, Groups, Graphs, Geodesics, and Gauges. These researchers are elegantly linking classical theory and machine learning and geometry and group theory to deep learning, which is fascinating. Now, the proto book is beautifully written, right? It's presented so well. It even has some helpful margin notes, and honestly, I could read sections of it out loud on MLST with scant need to change a single word. It's that well written. I mean, there's a lot of maths in there as well, let's be honest. Can't dodge that. But I often try to impress upon people that if your writing sounds weird when you say it out loud, then you're probably writing it the wrong way. But these guys have written it really well. Now, they've essentially created an abstraction, or a blueprint as they call it, which prototypically describes all of the deep learning architectures. The geometrical priors that they have described so far, they don't prescribe a specific architecture, but rather a series of necessary conditions. The book provides a mathematical framework to study this field, and it's essentially a mindset on how to build new architectures. It gives constructive procedures to incorporate prior physical knowledge into neural architectures, and it provides a principled way to build future architectures which have not yet been invented. The researchers have also recently released a series of 12 brilliant lectures on all of the material in the book, and I've linked these in the video description. Now, what are the core domains of geometric deep learning? So in geometric deep learning, the data lives on a domain. This domain is a set. It might have additional structure, like a neighborhood in a graph, or it might have a metric, such as what's the distance between 2 points in the set. But most of the time, the data isn't the domain itself. It's a representation, or it's a signal, which is on a Hilbert space. Let's talk about symmetries. Symmetries are really important to understand this framework. So a symmetry of an object is simply a transformation of that object, which leaves it unchanged. Now, there are many different types of symmetries in deep learning. I mean, for example, there are symmetries of the weights. If you take two neurons in a neural network and you swap them, the neural network is still graph isomorphic. There are symmetries of the label function, which means that an image is still a dog, even if you apply a rotation transformation to it. Actually, if we knew
That's all good. That's all fine and good, but it's 3 hours long and not what I want to do. So at the moment, so let's go back to what I was trying to do. That should be suffice to start it then. Or should be sufficient to start it. Oh. Hey, how's it going? Yeah, hey. Well, I'm streaming now again. I'm back to doing the DUI for the chatbot to chat with Bitcoin SV repo. It's running. Yeah. Yeah, I'm streaming on X. It's, I hope so. Chat with your code. See it opened up. Okay, so now what? GitHub repository URL. Nice. Yeah. Well, more people are definitely using it, that's for sure. More people are using crypto, that's for sure. And more people are doing NFTs. So it's a matter of seeing if we can actually grab back part of the market from the others or not, or if they're just going to say, yeah, that's cool ideas, let's just steal them and make it on our own chain. I don't know. I mean, I think it's a matter of like, what you got to do is just try to do the best you can to try to beat out the competition and hopefully get a piece of the pie. I think that we have a chance to work on some very serious problems, like stuff that other chains aren't secure enough to do, like healthcare records, things like high performance computing, scientific computing. Those areas are areas that people in the other area, the blockchains aren't qualified to be able to support yet, and probably not for a while. So there's a lot we can do there. I have an error, I'm not sure why, or connection adapter, because I have something set up wrong, leave it. Okay, I have to double check the back end and figure out what I did wrong there. So we have like multiple ways of talking to the repo. Let's see. Well, certainly, if I can figure out how to use it enough to make enough money to pay my bills, so I don't need to get investment, then do you think I would do it? Probably, right? So that's the thing. Well, that's the thing is that I've been using all my money to try to get my company up and paying for like fees, license fees for software. So I haven't been using it to trade, and I just bought some Sol the other day to try to use it. So I mean, if somebody can make like $25,000 in a few days trading Sol, if I could actually do that, well, I would do that. I just because I might have to do that just because I have to pay bills. I have to pay my rent. I have to pay for the Lightning AI contract that's coming up, and I have investors I have a potential team through Newer to get investors, but we still haven't discussed it yet because he had meetings in Montreal, and then he forgot his phone in Montreal, and he had to go back and get it, I guess, and so he was delayed. And we're gonna have a Zoom meeting today, and as he said, we do have a Zoom meeting today, but we're still not gonna meet until Tuesday. And I have to talk to him today though about whether or not we're gonna be able to pay this contract, the first deposit for the first month at least. Because it's just $12.50, it's nothing. But I still have to pay my rent, and I can go without paying it for a while, but I have to stretch it out. Yeah. Well, I was talking to other people, and it's like, they want to start working together more and more, but it's a rush to try to prove that we can do it. We made a deal with Amazon, we made a deal with the AI through their Amazon program just yesterday. And we're the first Bitcoin company to do it. In fact, we're the only Bitcoin company and the only blockchain company I know of that is actually doing it, that has a deal with them. Yeah. That's kind of what I'm doing. That's kind of what I'm doing. I was about to put my stuff to protect it and start saying, hey, if people want to get training, I'm going to provide training. That's what exactly. I was thinking about doing a course, I'm getting a paid course because I'm not making any money this way. Mm-hmm. With AI especially. Mm-hmm. Right. Yeah. Yeah, there's another thing I started working on years ago there. That's WebRTC virtual chat rooms. That way you can actually have you can actually do teaching. So you can do guitar lessons, you can do any type of lessons that you want and get paid. So imagine, the tempo example is a good example of how to do it. The tempo example that Project Radish put out, instead of being songs, there could be WebRTC streaming videos. And it's they're just streams. So there's no data storage or anything for that. Well, there could be data storage for it. It's not the intention. The purpose of it is to do live stream connection with teachers around the world, or to have chat rooms, conferences, things like that, live conferences, live communication, playing video games. Eventually move into storing videos. But just like a lot of streaming companies, you charge extra for storing videos. If you want to make NFTs out of frames, you can do that too. It should just be digital goods and services. Yeah. Yes. It's so like actually like having like credits over time. Like I mean, a teacher can give a course and actually say like this is like the formal music course. Right. Yeah. Mm-hmm. Right. I think part of the problem. Right. There's stuff like Saddle Learn or whatever, which is actually like pretty good for courses and stuff like that. But what I'm thinking about is like literally a one-on-one video courses, right? Like we're streaming, like so you can pay anybody for streaming. People are going to turn that into porn sites though, which I don't care if they do actually. Mm-hmm. Yeah. I tried that. You know what? He didn't want to give me the help because I bought like 6 or 7 Shua, and I said, I like that. That basically gives me like all these hours for your help that you can help me on my project, and he didn't do it. He refused to. He didn't want to help me. So because probably because he just doesn't like me. One of the reasons why he doesn't like me actually is because when they did the burning of the Money Button version, I had some Shua that was locked in Money Button and I couldn't get out because of technical problems with Money Button. And I told them that like if they went ahead with the burning and refused to accept my token and transfer to RelaX, that I would have to sue him because he couldn't get away with that. I said, you know that I'm having technical issue with Money Button right now. I've told you multiple times. I can't convert to RelaX right now because I can't retrieve my Shua, and you're gonna like cause me to miss out. And fundamentally, you don't even have to do this in the first place. It's really just a money grab. So what you're doing is you're gonna burn the original Shua and cut me out of profits, and you know that it's happening to me. And if you do it in this small community, everybody will know that it's basically on purpose. So you can't. Yeah, there was an exchange, and you had to do it, otherwise you would lose your Shua. Now, somebody said you could keep original Shua, but you'd never be able to use it. You'd lose it. Yeah. Right. See, the thing is that I was like right there the very first minute that he offered people to test it. He said, "Here's a test token." And I was like, "Give it to me, yes." And he gave me. I paid. I can't remember how much I paid, but I got like 5 or 6 for like 25 cents each, 26 cents each, and they went up to $10,000 each in less than a month, 28 days or something like that. So like 10,000 Canadian. It was over 9,000 American. So needless to say, I knew that as soon as the relay access burning started happening, I started offloading dumping it because I knew that it was just going to be dumped. And that's what happened at Relay X. It was just a pump and dump over and over again. Yeah. Well, he got upset. I even apologized to him one day. I apologized to him for it. I said, like, thank you so much for like finally accepting my shoe because I got the money, and I was like, I really needed it, right? There's another like 20 grand or something like that because I had two of them that were stuck or something. And I said, thank you because it means a lot for making it. I mean, I have return investment over 100,000%. That's really seriously. So no one that I know of has ROI that high on anything. If I have not, that's just crazy, right? It's like just think about it. 26 cents up to over 9,000 US. In 26 Canadian to over whatever it was Canadian, it was over 10,000. It was 11,000 actually. Canadian. And I was mind blown. But that's why I was panicking when I thought he said he was going to burn the stuff, and anybody who had the old children visa stuff behind. I was just like, no way, man. You can't do that. Right. He could have just made a new token. He could have just made a new token out of Relay X that was separate altogether. And then the money body show could have stayed maintained its price. It probably would have gone up to 100K. But think about it, in a year, it might have gone up to 100K just for being the first. You did it. Yeah. Now, there was some benefit to all that stuff happening, but there was also some detriment to what happened. And now we know because we see the shit from casino. It's like there's a certain amount of like negatives to it, but there's also positivity too. I mean, like if you have a creative idea that gets the people the joy and whatever, then that's enough to be valid, right? So like the whole meme thing, I don't have a problem with it per se. I just hope that it's not the only thing that we do. I don't want it to be the only thing. I just want it to be like, yeah, like I like the PFPs. I think they're pretty funny. And like I like the generative art when it's done the right way. So I don't have a problem with it. So don't get me wrong. I'm not like. But what I'm talking about really when I say shitcoins is I'm talking more about the technicalities. Like the lack of performance, the lack of scalability, the lack of the high fees and the lack of security that are present in some of them. That's what I'm. Yeah. Yeah. Mm-hmm. Mm-hmm. There's some people that think that they can tell when somebody's lying very easily, and they assume that there's lies being told by Craig Wright, but I don't see that. I just don't see it. I don't know if it's me or if it's them that's wrong. Mm-hmm. Yeah. Right. Yeah. Mm-hmm. 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 Right. Mm-hmm. Yeah. Right. Mm-hmm. Yeah. Mm-hmm. Right. Yeah, right. Well, here's August 3rd, 2021, tree signatures by sCrypt. We present the efficient implementation of multi-step with enhanced privacy using a technique called tree signature. That's an event. So it's possible. And they're composable. Machine learning marketplace on Bitcoin. Machine learning marketplace on Bitcoin. That's people care competitions. You see, we could run machine learning competitions on Bitcoin if we had AI on Bitcoin. This is what I'm pushing. Here's what? Yeah, well, I mean, I disagree with him on a little bit of stuff because the thing is that some of the stuff that he claims that he's claiming patents for were actually ideas that were out a long time before him. Like before he even came out as Satoshi, before he even was Satoshi. Stuff like that Hal and other people like me talked about in the forums of Everything List a long time ago, back in 2000. So I mean, honestly, to be perfectly honest, he is a little bit of a ego guy because he often will say that things are like that he came up with were only him. And what he needs to do is just realize, be a little bit more clear about the fact that certain other people like Hal Finney had, a full decade of experience trying to develop digital currency before he started coding on Bitcoin. A full decade, at least, of trying to develop digital currency. That this was something that Hal was obsessed with. Yes. Hal was involved in so many of these projects trying to get them started. And that's why he was there. That's why he was so eager to start using it when it came out, to try to see if it worked. It was something that he was deeply philosophically interested in too. The nature of the human consciousness. It matters. They studied something called the universal dovetailer argument with Bruno Marchal, who basically says the amoeba is immortal and biology is like, computation too. So we should really think about that. And his conversations are so long, they've had to cut them back many times over the years. They're like, it's impossible for anybody to consume all the information that they've posted over the years and everything else, because that's what it is. It's everything. It's like the theory of everything list. And yeah, you go to Google Groups and do a search for everything list, or it's just inside that crypt. There's another group that had cryptography and had some of the people crossover from everything group. The everything list is in Google Groups, yes. That's where it is nowadays, because they bought everything Usenet. The universal dovetailer argument. Yeah, I actually have a link somewhere here and actually saved, because I have all my favorites saved here. Just let me get it for you. I have to open Chrome. I just gotta find. See, in 2000, I wrote an article called, or a Usenet post called "Factoring Large Numbers." I think I figured it out, and I thought I developed an easy method for factoring large numbers, which I did. But the mathematics behind it actually worked, and people didn't know about quantum computers back then, or DNA computations, and making obscure type of computer models. And so they kind of harassed me about it. And Satoshi's the one who figured out how to actually make it work, because with miners. But it took 9 years. It took 9 years for somebody to come along with the solution. So the very same day I posted that factoring numbers thing, there was another conversation about double spending. I have the conversation started. It's like started conversations. I'll even just so I'm not bullshitting you here. I don't know how much of our involvement in the past Craig used, okay, or if he just let Hal use that information on his own. But Hal was visiting the site and talking about things like Boltzmann brains before or during that time, right when Bitcoin was being written. And we know he was working on it. So, like, I just... A little bit, but that was a long time ago. I was young, and I was mostly a lurker. I think I wrote like a couple of messages. Well, I think that he would want the blockchain to scale up to general purpose computation, because that's kind of where he was at. He just wanted spam protection for a while, temporarily, until the group's strong enough. It should be strong enough now. People try to steal from you, that you have legal recourse